So I'm going to present basically a small tidbit on internally insulating brick, but more specifically, trying to answer this question: will your brick last? So, some context. My wife and I, 6-7 years ago, bought the house of our dreams. And real shot. Freddy Krueger room, I like to call it. Clearly, it's the house of our dreams because we were a very limited number of people that went perfect, because there's only one solution, and that's gutting it. And so we did. And so we exposed the exterior brick walls. Traditional Toronto 1918, 1895 type double brick, above grade triple brick foundation house in Toronto. Exposed everything down to floor joists and the roof. At one point, that's actually after a little bit of work happened. But I had 2 contractors almost fall through right here, because I had a little piece of plywood and it was winter, so I had stuff over, and I said, watch your step. And I literally had to catch them. So you could stand on the first floor, look up to the 3rd floor underneath the roof sheathing. So what are we going to do? Building science prof, if I was, it was like more of an exercise in planning, because decisions were like this. The project started and finished within 4 months. And so I had to make these decisions really quickly. All this knowledge and quick decisions. So fast forward, we framed on the inside, and I knew for sure whatever I wanted to put back, I wanted a nice thermal plane. So took the framing out. It's 2x3. At this point, I knew I was going to foam. And we did. We locked in these 2x3 studs, good for drywall. And this is the context. So we have spray foam, internally insulated, historic brick masonry. What happens? And this is literally what I said after. Uh-oh, what happens? And, from a research point of view, that's probably not the best way to do research. But from a project point of view, as Greg alluded to, this is my research house, but it's also my home. So we bought it, we signed the papers, and I turned around to my wife and I said, oh, by the way, did I mention this is going to be a research house? And then I can't say what she said on the mic. And I've had some really cool research projects come through this house. And one of them was done by a graduate student of mine, Blair Williams. He graduated about 1.5 years ago. And it was on this question of what is going to happen, if anything, to our brick masonry, but more for the city of Toronto or other typologies in a similar vein of this. So, as you can see, this is just a mid-construction pic. We're interested in the brick masonry part, and essentially that condition, the 2nd floor, it's brick all around, all the way down. So, what's going to happen? What you can also see from this picture is that it's typical downtown Toronto siting, where I literally, just before we bought the house, I did 2 things. I checked if my canoe could go down the side, and I checked if my double bike that I used to drive my little babies around, there's this way I could go down the side. So the key is narrow laneways, which is a huge key. If you actually look, my neighbor's roof is, their eaves are really close to here, and on this side, same. So that's a very, very good key piece of information that you want to remember for the next 10 minutes or so. So we needed to monitor the brick. What I'm going to outline in the next 10 minutes is a method that others have and we have been doing and furthering using something called frost dialometry. And essentially, before I tell you and show you, I'm just going to give you a pictorial narrative here. It's taking a brick, slicing it into little brick pieces of bread, and then measuring some characteristics. And I'll show you, hopefully, you get a good feel on what's going on. Because we're 15 minutes here and it's not, a master's or a PhD thesis, I'm not going to get too technical, which I think is fun, because then you're not going to get too sleepy. But if you're interested in more information, you can email me if it's research. And Greg gave me a nice little name tag, and you can email me if it's paid work, because I do both things. So, what you want to do, basically, is take brick out and figure out what is going to happen. This is a blank graph, and as you see, or some of you can, some of you can't, basically it's moisture content on the bottom, 0 to 100. Clue number 1, what? 100% moisture content? That's impossible. Well, 100% relates to the maximum amount of moisture this brick can hold, not gravimetric moisture content, which usually, 16, 18, 14%, that sort of thing. So 100%, literally, it's normalized. Max amount of moisture at 100, bone dry at 0. Then you have something called microstrain. And if you're not an engineer, or if you haven't done any physics lately, basically that's movement over standard length. So movement related to moisture content. That's what we're measuring. We're trying to figure out how a brick moves destructively, at what point it destroys itself, based on the moisture content, during freeze-thaw cycles. That's the key, that's the context. Because that's what we're worried about. When we insulate from the inside, all of a sudden this brick that used to have no insulation, it's like a little easy bake oven house, and we're the little light bulb inside, internal gains, furnace, etc. And it's, just warming up the brick. And who cares if it gets wet? Because it's just easy bake oven, dry, dry, dry. Once you put the insulation there, bam, that easy bake light bulb's doing nothing to the brick. And you can actually move in the freezing plane, and some of the exterior or interior brick wads can be susceptible to more freeze-thaw cycles. But it's not just the freeze-thaw cycles that matter. So what you do is you want to test it so your brick doesn't end up like, this is not my brick. This is another project I worked on. This is not even as bad as I had. I just couldn't track down another picture. You don't want your brick to end up like this. This is the question we're ending, or we're going to end with answering that question a little bit. The story continues. So these are bricks from my research house, and you basically take whole bricks out, slice them into little brick bread slices. And in the lab, you can do this to new bricks too. It doesn't matter if it's hollow core. Obviously, you get more samples from a hollow brick than you do from a modern core brick. You take those little bread samples and you put in a little drill press with a nice little widget, and you put little pins in. These pins are going to be pin on this side, pin on this side. This is how you measure the microstrain, because it's microstrain. It's a tiny bit. And then you're going to weigh these things bone dry. That's what's going to give you your 0%. So put them in an oven for 24, 48 hours, 0%. It's dry. Do we know? Well, you can play around with it. But yes, you're going to believe me. We know. Then you rig up a vessel and add some moisture, liquid water, vacuum, peristatic pump. You basically put the brick samples in here, add water, make it pressurized, and you're forcing moisture into the pore structure of the brick. You want to get it fully saturated, super saturated, if you will. Okay, beyond passive 100% moisture content. You want it to be like, basically you could do this or a 5-hour boil test, which is exactly what it sounds like. Brick and water, 5 hours boil. You're just pounding it. And then you get the 100%. So that's what I mean by normalized. 0 bone dry, 100 as much water as you can put in this brick. Then the fun stuff comes. Then, these are real pictures out of the lab. You basically say, at 0% moisture content, 20, 40, 60, 80, or 100, if this brick goes through some freeze-thaw cycles, at what moisture content does the microstrain basically go and show that your brick has basically moved and will never move back to its original form, thereby being destroyed? That's our criteria here. We don't know where that's going to happen. We don't even know if it's going to happen at 100. Chances are it's going to. But we know, assuming it's going to happen at 100, we need to figure out where it's going to happen. 20%? Probably not. 40? Maybe. Weak bricks? 60? Probably. 80? Most likely. And then somewhere between 80 and 100? Almost definitely. That point, whether it be 20, 40, 60, 80, 100, or somewhere in between, that is called the critical degree of saturation. I think the name explains itself. Below that, you're good. Above that, you've destroyed your brick. So the next step is we know how much this little brick sample can hold based on our pressure test. We know how much is dry. So we say, 20%, 40%, 60%, 80%. And we just literally get a little dropper, and we go, how many drops are 20%? You put it in, you wrap it up, and then you put it in the freezer we rigged up to do freeze-thaw. You do that for 20, 40, 60, 80. Somewhere between 60 and 80 maybe, you see it bust. 60's fine, 80's not good. Then this is the boring part. You repeat. Was it 60? Was it 65? Was it 70? Was it 75? Depending on if it's research or how much the client has in terms of budget, you could go, it was between 70 and 75. Oh, was it 70, 71, 72, 73, 74, 75? You see where I'm going. You put it in this fridge, and these are actually, just to make sure our fridge was working, plus 30, minus 30, 9 cycles over a couple of days there. So it's working. So you're basically putting it through 9 freeze-thaw cycles. 6, 9, 12. There are standards that tell you can make the judgment. And eventually you get that plot that we had, and you start to get a curve like this. There's your proverbial hockey stick. 20, no problem. 40, no problem. 60, relatively no problem. Something's happening. 90, not happy. 100, I think we already broke the thing and basically it didn't move anymore, sort of thing. So that's in the industry or in research what we call a point that we're just going to ignore. But clearly, you can visualize where the critical degree of saturation is. And you do this not just for one brick, you do this for a bunch of samples. It's project specific, but you do it over and over again until you get a level of comfort that you're happy with. And then eventually you get to this point, engineers like to draw lines through points. So you draw a line through a point, and then you go, 75, 74%. There it is. It's not 73, it's not 76. You have to take it with a grain of salt. But somewhere around there, it's a critical degree of saturation. And this is just an example, a real example. This is another one. So it does move around. A bit subjective to where you draw the red line when you're presenting a research or to a client. I mean, for me, I could have probably drawn it this way, but I want a bit of, engineering school back in the day is about factor of safety. So I'm drawing it that way. It's tough. It is a bit of a black art. At the end of your project, you want to basically understand what the observed critical saturation is. And then sort of a backstory is what's the dry weight, what's the max moisture at saturation that you added. So that's our boil test. And so you can kind of figure everything out. And where does this happen? So that's the lab part. Take brick out, cut it into slices of bread, figure out the critical degree of saturation. That's great. You can go running to the high hills going, it's 70%. And people look at you like, what does that matter? And you're like, it's 70%. And it doesn't really matter, because what does that mean? Nothing. It means 70% of normalized 100, you have problems. But how do you relate that to the real building? It's funny I say that since there's a fake picture of my house up here. But this is because we show some of the monitoring locations. And this is the second half of the presentation, relating the lab results to field results. Now, I could stop here and show you simulations in WFI, because it's the same idea. But if you have in situ data, let's keep on the natural path. And in this case, we do have in situ data, and we have a homeowner who is very, very supportive of research. So these are this is north elevation facing the street. I own the east side, therefore that's where the sensors were. A couple on the west side, a couple on the south as well, where you're going to get sun. But this is what we did. We basically picked locations. In general areas from where we picked some of the sample bricks. General. That shouldn't matter, might matter. And we used surrogate moisture content measurements. Basically, piece of wood that's calibrated, wires coming out, measuring, using electrical resistance, measuring the moisture content of the wood. So we're going to say for now that's of the brick. But there's a bit of a disconnect, right? Relating the wood to the brick. We'll talk about that a little bit. We did mostly, or all, above grade, so double withe. We got the collar joint. We got the interior withe, so this is inside here on the right. And then we got the exterior face. So really that's where you're going to have the most freeze thaw, presumably. And it looks like this. You take the exterior brick out, bring it home, or bring it to my basement, bring it to the lab, and that's where the first one. So that's the exterior face right there. And you put in your wood content. You try to, for various moisture transport reasons that we won't get into here, you pack it in brick dust. Because once you drill a hole, all of a sudden you've messed up the local area that you're measuring. So you have to try to put it back as it was, which is ridiculous because now there's a piece of wood there. But that's a whole other hour chat. Anyway, you put the sensor in there. And that's actually looking into the wall. So we went straight into the interior withe and up to the collar joint here. Interior withe, straight in, collar joint, up. and then we put the brick back. And a side note, Blair was a sucker for punishment, so if anybody's interested, we also took high-res pictures of all the brick. And you might ask yourself, why? My reasoning is, you know what? A picture says 1,000 words, and I think this is what Blair said to me once, and I said, aha, good idea, Blair. Why don't you take 500 pictures of all my brick so that we can make mega files, so that really, this doesn't look like it, but I could actually zoom into perfect clarity a brick surface of this big, like just bigger than a loonie, just to start to see if cracking and that sort of thing happens. Because visual confirmation in 10 years is better than anything any sensor is going to tell me. Unfortunately, it's too little too late, but still. So this is a side project. But what you can see here is the sensors were, these are the wires, I believe. So we just put the brick back, and we start to get data. So focus on moisture content. There's actually 3 sensors for the collar joint. Yellow is hidden underneath the green, and yellow is inner, collar is green. So not much difference between the collar joint and the interior. Exterior, we have some interesting results. This example is gravimetric moisture content of the wood. So for now, we're going to assume that that's of the brick, just for now. Well, for tonight. But 14 may be high, it may be low. That critical degree of saturation for those bricks at about 70 to 75, 65 to 75% that we figured out in the lab, that relates to a gravimetric moisture content for this brick of approximately 14 to 16%. If we want to put a little drama in this presentation, let's say 12 to 16, because all of a sudden, voila, 14 is right in the middle of that, and we go, oh no! But we have to put another texture. We don't need to put another layer on that. And that is, I don't really care if my brick moisture content is up there if there's no freeze-thaw cycles. Aha. So we need to measure temperature. And here's a bunch of temperature measurements. This is the basically interior. And exterior is here, very close by, the red one. And the outer withe, so the sensor, moisture content sensor, also measures temperature. The outer withe is the purple one. So in this case, we kind of go, okay, well, that outer withe went down and didn't go up again. So in this case, it might be going up here, and this might be going down, who knows. But in this case, one freeze-thaw cycle, not even a freeze-thaw cycle, one freezing cycle over about a week at potentially a critical degree, critical point. So bad, not so bad. The reality is the way the wood measures moisture content relative to the brick, the critical number for me here actually is about 20. And that's just because of instrumentation. So really, I don't have a problem here. But even if it was at 20, I may not be too concerned. It's only doing this once. This is right at the brick. Another location, same idea. It's a little bit, there's a couple of cycles here. There's 1, 2, maybe 3, arguably 4, 5. I'm even less concerned because my outer withe is drying. Not so much a problem. Another one, we have increase in temperature. Spring's coming over a couple of weeks. And this is interesting because, spring is, everything's melting. And so you see a little bit of increase over a couple of weeks of moisture content of that outer withe. Problem, it's just coming out. It's not going back below 0. So I'd say not so much. At the end of the day, I'm not too worried. This would be a pretty hairy freeze-thaw cycle sort of regime in here if we kind of went back. This is like January, a little bit of a thaw. But again, you're getting the picture here. I'm pretty low on my moisture content for the brick. So not that worried for this case. This whole method, this 15-minute presentation represents, the doing it right approach. Like if you really want to try to figure this out, this is the way to do it, or it's a way to do it. It's not very cheap, and that's why most people, if they ask me, okay, I'm internally insulating on my brick rust, so there, I'm this rust, and they go, am I going to have a problem? And I go, well, for X amount of money, we can figure it out in the lab, and maybe, you know, if it's interesting, we can do research, and if it's boring, I'm going to charge you, sort of thing. And I say, and they're like, no. You know, I always joke with people, I wouldn't hire me for a house because it's costly. And I go, okay, so totally off the record, as they told us in engineering school. So I go like this, I maybe go like this and swallow it, and I go, take a look at your downspouts. Take a look at the ground. How's the brick doing? Give me a picture. And I see their brick is looking like that brick in the beginning, I go, internal insulation, probably not good for you 5, 10, 15, 20 years down the road because the brick seems to be weak in high moisture locations, right? That's what most of us do. Or if they show me brick that's perfect and then they show me a downspout that's terrible, I know that that's been loaded with moisture, lots of freeze-thaw cycles, super saturation, and the brick's still doing well. I'm like, brick's looking pretty strong. I haven't tested anything, but you know, that's my unofficial opinion. So that's the easy way. This is the way that should be done. Am I worried about my house? Not so much. At the end of it, you can get freeze-thaw cycles. You know, you see some trends that you would expect. East, north, south, south more. East, north, kind of similar. East, slightly more. But again, without understanding the moisture content of the brick, this kind of quantitative data is not as meaningful as it can be. Right? We don't necessarily care about freeze-thaw cycles. We care about the intersection of freeze-thaw cycles, the strength of our brick, the moisture content, etc., as we spoke about up to now. So am I worried? No. This is after. This is like maybe 2 years ago. The house is still standing. The brick's looking okay. I moved on to do weird and wonderful things on my roof, and you know, I'm not too concerned. 20 years down the road, I think I'll still be telling the same story. Not too concerned. However, back to the beginning, my house is fully sheltered. The actual amount of brick that's fully exposed is, because of the renovation, is a tiny bit on that south face. That mid-construction picture, we bumped out the kitchen. So it's just a tiny little bit below the third floor and above the second floor. It's exposed to water. Everything else is practically covered. In fact, the worst brick for me, I still have to fix it, is at grade because somehow my neighbors managed to slope, back in the day, both side laneway concrete to, guess where? My brick. So, you know, if I put a nice V and put it down the side, it won't be a problem. So I'm happy. Hopefully you got a good understanding, a little tidbit, a morsel of what you can do to answer that question that I posed at the beginning. It's neat stuff. It's always fun. I'm open to discuss this with you in the future. Unfortunately, I apologize. I need to run out to a familial obligation, so I'm literally going to keep walking out that door. But you can look at my contact details, and if you want to discuss this further, by all means. So thank you very much for your time, and hope to see you again.